k-fold cross-validation. So how does a k-fold cross-validation set works? So you can see here you have a complete training set. We have a complete training set. Now, what we do is this. We divide the data set into training fold. Can you see? We divided training fold and test fold. Now, what does it mean? This means that we have now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 fold. Cool? That is why it's K fold. So you divide the data set into 10. Now you train machine learning model on this fold and test its performance on this one. This means that the machine learning model in this case have seen all instances here when you train. Now you go to another iteration, then you select this fold to be the test set, but you train machine learning model on all other fold, 1, 2, 3. Can you see that? You move again. Each fold can be a test set. And now up to the 10th iteration, you can see here, this is the test set, and all this part is training set. This means that we solved the problem where I said, when you select this as a training set and validation set and test set, it solved the problem where the model only is sensitive to the way you do the division. So in this case, the model can be trained on every. So how can you do that? Now you have 10-fold. Then you find what is the accuracy here, E1, E2, then you find the average. So you find the accuracy, the model accuracy in first iteration, model accuracy in test, up to the 10th iteration, you find the accuracy, and now you find the average. This is called k-fold cross-validation. So k-fold cross-validation basically allows you to divide your data set into 10 folds.
Sorry, Doctor, then come again.
Yes. So k-fold, you have a training set here, one training set. Can you see that? What we can do is you define how many fold you want to divide your data set. Some of the people in literature, 10K fold is widely used, 10. Meaning you need to divide your data sets into 10 classes, 10. Can you see that training data? Can you see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I divide it into 10, right? I divide this training set. Can you see? I divide, this is a training. So this is it. You have this training set and testing set. So this training set, same with occasion. This training set, we need to take this training set and now divide it into 10 division. Now, if we divide it into 10 division, 10 fold is called folds. Now you train your machine learning model in this 9 fold and validate on this 1 fold. That is this idea. Train, validate. But your test set is there separately. This is train and validate. Now, this fold serves as a validation set in this first iteration. In the second iteration, you select the next fold and all other ones to be part of the training set until you have 10th iteration. Why do we have 10th iteration? Because I divide my data set into how many fold? 10 fold.
10.
Now, so what is the accuracy of my machine learning model on this first iteration is E1. What is the accuracy of machine learning model on this fold? That is, I train my machine learning model on these 10, this, and this is evaluation is E2. Now you have 10 accuracy. Now, since you have 10 accuracy, then you find their average. You sum them and divide by 10. You get a single number. That is what you take as your stuff. I don't know if you have another question.
Okay, so this means all these 10 folds is on the training set alone. Oh, if I understand what you're trying to say, you divide it into 10.
Yes.
You train with 9 folds and then test with 1 fold.
Evaluate. Yes, because it's evaluation. The test set is there separately, because look at it. You can see this is the training data. Can you see that? Here we have 4 fold, 1, 2, 3, 4, 5. This is the test data separately. Got all data, got data, enter. This is the data. Now you divide it into training data and test data. So this training data is where you divide, you do this kind of fold stuff.
Okay, so sorry. Wannan shine kaman raba da ake gida uku din nan, test, validation and train, validation, and test. So the train, the validation, our basic.
Yes, so we already discussed this. We have the first method that we discussed is called hold out. You only divide your data into train and test set. We say it has problem. Yes. The next one we say, okay, let's do this. Divide into three: train, validation, and test data. But it turns out that this one also has like some problem, where the problem is if the training, the division of the data set affect the performance. Meaning here you can see I have one data set. I divide this first half to be training, this section to be validation, and this section to be test set. Now the problem with this is that if you now take some part to be trained, so let me assume that this part is now my train. This part is now my validation, and this part is my test. Then the accuracy of the model will be different. So this method has a problem, is sensitive to how we partition the data. That is what a disadvantage of the hold out method is, that performance estimate may be very sensitive to how we partition the training data set into training and validation. So it's very sensitive. So for example, now here from here to here, I said it's training set, from here to here is validation. Now, if I say from here training set to here is my validation set, it's my training set, then the performance was, it depends on how you do the, so we said, okay, the best way is to do what is called cross-validation, where you take some part to be trained, you take some part to be validation, but it's still hold this training data. It is still this, and you are just, dividing those stuff. So that will solve the problem of that, because each part of the data set is served now as a training set, and now each part served as a test set, as a validation set.
Thank you.
Yeah. So this is it again, as we can see. This is all. This is all the data set, and we divide it into train and test set data. And now we have our fold, you can see in this case, this is five-fold. We have five-fold. And this we say, okay, this will be our test set. We train our model in this four-fold, and we validate here. And we have the accuracy. Can you see number one, accuracy number one? We train the model in this fold 1, fold 3, fold 4, fold 5, and now we evaluate the performance on fold 2. We have the accuracy here. Now, finally, what we can do is that you average all. That is, this is what we show here. Take the average. Okay, any question? So when we now...
Doctor.
Yes.
One estimated performance, that is E.
Yes.
Is it always accurate ko akwai error?
Yeah, always zai baka misali a wannan. So it is estimate. So when you say estimate, it means is not always like 100% correct, it's estimate. So the result you may get here, maybe here the accuracy you find is 67. Here maybe 68, here maybe 63, here maybe 64, because we have different fold, right? Now, so for us, if we have such kind of difference between different, then the best way is to take average of all the performance and give it as the accuracy of the model. I don't know if I answered the question. Do I attempt to answer the question?
I read it in the note. It says that estimated performance, which is I. So it's classification, either classification accuracy or error.
Oh yeah. So we can do two things. When you have this, so when you are doing classification, two things you can do. You can give accuracy when you do a prediction. That is, you can say this is the accuracy of your model is 69% or is 68. So for example, let me train a model. It's still the same. So let me explain this. So let me assume I'm doing classification. I train a machine learning model to do classification. I can say the accuracy, I can say the accuracy is 98%. Meaning, the error. Who can tell me the error?
2%.
2%.
Yes, exactly. Or 0.2 energy. Is it 0.2?
Yes.
Yes, so you can say the error is this. So the same thing. So that accuracy, that is error. So here we can say the accuracy of the model is this. You can give it in two ways. So yeah. So don't be confused when you are doing classification. Some people will give the performance in terms of accuracy. Some people will give the performance in terms of error. So here you can say, okay, the error is this, the error is this, the error is this, the error is this. So it's still, yeah. I don't know if I.
Yeah, it's okay. I get it.
Okay, yeah. Okay. So you can see here, we then calculate the average performance of the models on the different independent test scores. So here we calculate the performance. Yeah. Okay, so you can see here, you can do this. And now, yes, go on, question. Okay, so here, when we try to find which algorithm, because maybe you are testing different algorithms using this k-fold correlation, you are doing, you know, anyone. So when you, or you are tuning some parameters, when you find the best parameters, then you can, with the best, less error, if this is an error, with the best performance, then you can select that model. Now, what happened after model selection? So if we try different models, maybe different algorithm, and we said the one with highest average performance, then we select that model. Now, when we select one model and say, okay, we are going to use this model, then the next thing is put all the training data set, you put all this, don't use this fold again. Now you put all the training data set and train that model once more again. Because here you are doing what we call selection, model selection. You are trying to model, select different model, one model from different fold. After you select one model that performs best, then the next thing is you can put all the training data set in one fold, I mean, yeah, and train the whole model. So that is k-fold cross-validation. Any question? Okay. So in summary, k-fold cross-validation make better use of the data set than the whole our method with validation set. Since in k-fold cross-validation, all data points are being used for evaluation. A good standard evaluation for this is 10. So a good way people, when you are doing the literature, you can see people divide the data set in 10 k-fold. So you can see that in each iteration, the model have seen, you know, sample of the data set. That is one of the advantages. We also have another one, which is called stratified, k-fold stratified. So what is this one? So the problem is that let's assume.
Doctor,
yes, go on.
Under the highlight, leave
Where?
one out cross validation.
Under where?
The hint. Leave one out cross validation.
In the book, Kokuma and slide then.
At cikin book din only
Okay.
look Lucy viewer.
Let me go back to the book.
Leave
Okay.
one out cross validation.
Yeah.
It's
no,
a special case of k-folder across validation.
So leave out. So I didn't just include it here. So what this means, we have what is called leave one out cross validation, where in leave one, what we use is that we set the number of all equal to the number of training examples. So this is what happened. So let me show you. So for example, it's extreme form of k-fold. So let me show you an example. Let's assume we have a training data. We have training data. We have like tweets, which is 1,000 tweets. Can you see that? Oh no, don't. Why 1,000 tweets? 1,000 tweets. Can you see that? 1,000 tweets. Now I want to do k-fold cross validation. Now leave one out. What it does is this. I will select 900 and 99 to be my training set. And that one will be the validation set. Validation. Can you see that? Now, you now do another one. That is, okay, this one that I select to be the validation set is the Nadubudeng Shine validation from 1 to 99 to be training set. Now I find the performance of the algorithm, my algorithm. Now I select another 999 and another one to be the validation set. The validation set is not the last one, the second to the last one. So meaning here you can see, given training set, you divide it into fold you want, maybe 10. So if I have 1,000 tweets, if I have tweet guda dubu daya, if I divide them into 10, how many will I, in each fold, how many am I going to have in each fold?
100.
Yeah,
100.
So here would be 100, here would be 100. So it means you train your machine learning model in 900 and now validate on 100. In
100.
But leave one out. Why? You train your machine learning model here, the beginning is 999, and only the last one, you can validation. Then the next one, they're gonna there from 1 to 998. 99 thing will be the test set and the test set. I don't know if you get what I mean. So this is one for why, what is it called? Leave one out cross. It's extreme. So it's a special case cross validation. It's the leave one out cross validation method. We set the number of fold equal to the number of training example. I don't know what you mean. So here you can see if I have 1,000 data set, then how many fold am I going to have?
So 1,000 divided by 10, that is
Yes.
100.
No, okay. Excuse me. Baba na sharing the book, Mako.
Okay, Vakashi.
Yeah. Two things make it am sharing. Okay, just excuse me. Okay, can you see the book now?
Yes.
Yes.
So you can see, leave one out. It's a special case of cross-validation, is this guy. We set the number of folds equal to the number of training example, so that only one training example is used for testing during each iteration, which is a recommended approach for working with very small data sets.
Yes.
Okay.
Yes. So if you have very small data set, this is one. For example, you have like maybe 100. I don't know, like, you know. So if you have 100, you are going to have like how many? Sorry. Yeah. So that is the one. Yeah, so that is the one you are talking about, leave one out. If you have very small data set, maybe, you know, I'm not sure how small it is that you can do that, but the disadvantage of that is that it will take much time, you know. So if I have 100 training sample, and now I said, okay, I will use that approach, it means you are going to have 100 iteration, 100. But here you can see we have training set, we divide it into 10, then we have only 10 iteration. But if you have like divided into, you have training sample like 1,000 and you say you're gonna do that one, you're gonna have 1,000 iterations. I don't know if you understand, Kagan, I answer your question.
Yes, sir, it's understood, but I'm trying to make the difference between the standard cross-validation and the leave one out cross-validation.
Okay. Yeah, so as they explained, it's a special case if you have small data set. So for example, here, I have large data set, 2,000, maybe just very small, like 2,000 or 3,000. I can divide it into, 10. So 1,000 here, meaning each will be like 10, 100 in this iteration. But if, for example, I have, let's assume I have 100 training sample, and now that 100, I divided it into 10 iteration. If I have 100 training sample, 100, and I divided it into 10 fold, how many will each be in one fold?
10.
So 10. So the idea is like now I train my machine learning model in 90 and test in only 10. So the validation may not be well, may not well capture the true, So the idea is if you have very small, train on the 99, and evaluate the performance on that only one. Yeah.
Okay.
So on each sample, you try to predict. So you increase the chances of, finding the accuracy on each stuff. So that is basically the idea. So if you have very small data set, use that one. But if you have large, and which is always what we have in some sense, we always have like at least 1,000 or 2,000. So you don't need to use 1K for cross-validate. The other one, yeah.
Yeah, it's okay.
Okay, maybe you can also read more about it. Yeah. Okay, so yeah, we have another one called stratified K-fold cross-validation. So what is this stratified? Let me assume that here we have a data set which is male and female. Male and female. So you can see here we have few female, right? We have males there. Now, if I said I want to use this data set, male and female, to do cross-validation, like this, to divide it into different folds. So you can see that if I divide them into, it may turns out that when I do the fold, how can I make sure that each class is represented equally in the distribution? So look at the fold. Now we have 5 fold here. You can see here I divide in this fold, round 1. The female is now, each portion is still the same in each round. So I divide into 5 fold, 1 fold, 2, 3, 4, 5. So you can see that this male, idan nan 20 ne, to nan ma zai kasance 20. Idan misali, let's assume the male is 100, and we want to do five cross validation. It means we want to divide this training data into 5 classes. Then this will be 20, 20, 20, 20. Let's assume that here is 50. Then here will be 10, 10, 10, 10. So this kind of partition is in each class. This is called stratified K4. If you remember me stratified bar, meaning it may turn out that when you divide the data set, if you haven't done stratified, it can turn out that here around 1 here maybe, because here is 100, then here maybe can be 30, here can be 25, here can be 40, here can be, and kuma nan muna da 50, here can be 10, here can be 15, here can be 20 here. So you are not dividing the class equally. So we always put this stratified K-fold. So when you are dividing your data, you need to divide it stratified. I don't know if this, so you can see here in each one case you have this. I don't know if stratified K-fold makes sense. Do you understand code? Okay.
Yeah, it's clear. Okay,
so yeah, so this is basically K-fold cross-validation theoretically. So let's see how we can do K-fold in scikit-learn, which is basically very easy as well. Anyone want to add something? If you want to add something or question, please ask or add more explanation before we move on. Okay, so so let's look at how we can use cross-validation. So if we want to use cross-validation, remember previously we don't use cross-validation. We just divide our data set into training set. If you remember, we just divide. If you want to do, yeah, I think maybe here. Okay. Yeah. If you remember previously, we just called, yeah, train test split. You remember where it divides our data into train, test, white train, white test. This is what we have been doing. But now, Simakachi, this is not the best way. We will not be doing this because there are some issues with that. So now, how can you now be dividing your data set? So this is using cross-validation score. You import it. While we were doing the other one, what we import basically is this. We import train test split. You can see Sklearn from model selection, we import train test split. Now, we are no longer importing train test split. Still from model selection, import cross-validation. So here we create a pipeline. You remember our pipeline, make pipeline. We do that. We said simple imputer, we want to do missing value. We want to impute. These are transformers, the transform. We do the scaling. And now we use PCA. And now the final algorithm we want to use is logistic regression. This is what we have seen last week. Anybody that doesn't understand this one, anyone with question regarding this, ask question before we move on. Yeah, so it's good to read the book because I can see who is asking the question. He has actually read the book and he will understand more better if you read the book because you can see he's asking some question. So here, don't forget, I'm just going through the book, right? I'm copying everything in the book because it's just discussion among us and you learn more by reading the book. So I urge you, please read the book, practice, and you can ask more questions. So here we make pipeline. Now, after the pipeline, what we can do is we fit on train and white train. So we fit our pipeline and now we can make prediction. This is a pipeline we can on test data and we can find a score. Remember on X set and Y test, this is where you can find a score. And we can print accuracy, test accuracy, right? We can see this test accuracy, I print it. And this 3F, meaning print 3 significant digit, right? That is why I use it. This is called, we all know this is F string formatting, where you just put F. Anybody that doesn't know what this F means? Anybody that doesn't know what this means? Okay. Please don't feel shy if you don't know anything. Ask, we are all learning. So here you can see that. But any question? Okay, no question. Okay, so here you can see we want to do basically use cross-validation here, right? We want to use.
Sorry.
Yes.
Sorry about the cross-validation. Is it because we are trying k-fold that we are no longer using the splinter train test?
Yeah, so here you can see I have my train set. If you already have your own, here I have my white train. Can you see this white train? If you go back to cross-validation, if we have our data set, can you see that? Can we see we have all our data? We divided it into a train and test. So when you are using cross-validation, you can still use, we will still use the train test split to divide the data into train and training data and test data to do the division for that, because test data is not used in our k-fold whatsoever fold, right? It's not used for that. So here we can see what we put in this cross-validation score is X train and Y train. And here, how many cross-validation you want to do? I said here 10. I want to do 10 cross-validation. And N jobs, it means if you have, your computer has, 2 CPU or 10 CPU, because this is tasking, maybe I'm doing 10-fold cross-validation and your computer has 10 CPU. You can say N jobs mean 10 CPU. So each task will be sent to one CPU. So for example, me, I have 10 core CPU, my computer is 10 core, I can put 10 here, right? So if you have only one, you can even put only -1, so that the computer will use the available jobs you have, available cores you have, so that this is just meant to make the work faster. So yeah, and we can see here cross-validation accuracy score. We have this. you have this. So here you can see I use normal one that we have been using in scikit-learn. We basically feed the data, and we basically do this one, which we have already been seeing, right, in previously. But this is a new approach using cross-validation. You can see we call cross-validation. We put our estimator pipe L, which is this. This is the estimator here. You can see it, that we create a pipeline. And now we put the train, we put the Y, we put the how many you want to split. And now we find the accuracy now here. And you remember here, because we are doing 10 accuracy, how many results are we going to have? We are going to have 10. So you can see 1, 2, 3, 4, up to 10. This one is the accuracy from the top one. And now we can see here, as I told you, we're going to have different accuracy. You can see 1, 2, up to 10. And now you find the average of all of them. So how can you find the average? Here you can see we can take the mean. So you can see here, I say, okay, n-feeded mean score. Remember, this is NumPy. Mean means a function to find the mean, that is average on the scores. This is the score. Can you see the score? So this calculate the 3F means 3 significance. You can see this is 0.950, right? 950. So you can see this performance cross-validation accuracy 950. This accuracy that we know, we just use the train set and test set to divide the data set into 2. You can see it is accuracy 0.956. Yeah, so that's yeah. I showed if you want to find how many cores do you have in your computer, there is some function here from multiprocessing in Python, import multiprocessing. Now here I call multiprocessing the CPU count, meaning show me how many CPU do I have in this computer. So you can see I have 10 core CPU. So yeah, this is basically, so you can see here, you're gonna use this cross-validation if you want to train machine model. Anyway, you don't need this. So just create your pipeline, make pipeline, and now you can just do it like this. Print the train set, Y train, and now you put the result, the accuracy score. Any question? Okay, so, here yes.
From the list, from the results we've gotten above, we can see that the accuracy of individual faults is different. You can see that there's 97 is somehow high, or higher than the others. So what does this mean? Does this have any meaning?
Yeah, so that is one thing that this K-fold try to avoid. So if, for example, we just use only one way to divide the data into train and validation set, now we're going to have only one result. And that one result may be different if we divide the data differently. So you can see here, one fold has 0.93, you can see 93, but another can you see 0.95, 0.95, 0.9. So you can see each fold may have different, because we have different instances in each fold. So the accuracy may differ. Do you understand? So the accuracy may differ. So the best way is just to, this is the idea, even the idea for the K-fold. So the best way is to find a single value, is just to sum them and find their mean. So you can see here, we have the mean 0.95. So finding the mean across 10 fold, you can see the mean performance is 0.9. Instead, if you are using only one fold, maybe you just divide your data in train and validation, you only have this performance 0.93 because you are doing only one. So you can see, but changing the data, you may have different results. So this is the idea of K-fold. Any question again, or anybody want to add something? Right. So then debugging algorithm with learning curves. So this is something also very useful when you're trying to deal with machine learning. You know, there is what we call learning curves and validation curves. So they are used to basically solve the problem of overfitting, high variance and underfitting in learning curve, and we can see that. So let's recap our overfitting. So when we say a model is overfitting, it means the model is very complex and it fits training data perfectly. That is overfitting. We did this, meaning that the model, fit given training data, it fits it perfectly, and performance accuracy maybe is 100%, 99, 90, very perfect, perfectly. That is a model that is overfitting. And when the model is overfitting, if you give it some training data outside of the training set, it may not perform well. So any model that has overfitting, it means it has high variance, meaning on the data set that is trained, it performs very well, but cannot going outside of those data, you give it, then it will perform worst. That is, it has high variance and it does not generalize. That is overfitting. Now, underfitting, that is model. If a model has underfitting, it means it has high bias. So a model that is too simple, even the training set does not perform well on the training set, talk less of the new data. Then this model, we say it has high bias. So having this stuff, bias and variance, how can we find out if our model has bias or variance? Now, if it has high variance, so if at the end, before you want to find out high variance or variance, so you can diagnose that with what is called learning curves. So we all know that if model is complex, they fit in data. But if your models is complex, one way is, as we have seen last week, is to collect more data, which is not always feasible. But let's see how we can do something better. Now, let's explain what this means. So I have model and I float accuracy here. So accuracy starts from 0 to 1. So if I say my model accuracy is 1, it means it's perfect model, 100%. And now here you can see I float number of training sample in my data set. Maybe here I have 100, 200, 300, 400, 500, 600. So, you know what I mean? Now, this is your desired performance. So you want to train a machine learning model, you should have okay, I expect this model to have maybe minimum accuracy of 80%. So here, this is what you expect your model. So you can see here, desired accuracy. This is what we expect your model to have, desired accuracy. If the model does not perform up to this, then the model is no good. If the model performs close to this, then the model is good. So what we can see here is that we have number of training sample. So the number of training sample we can see here in training accuracy, we can see training accuracy. So training accuracy we can see here started from here. Before it's maybe, I think maybe 0.5, but the training accuracy at its start from the number of sample, maybe here is 100. This is the training accuracy. When we add more data, 200, the training accuracy is dropping. When we add more training sample in the data, the training accuracy is dropping. But we can also see that for the validation, which is this validation accuracy, it starts very low, but we can see for the validation, with more data is increasing. But we can see here that the training and validations, they all reach to plateau. They plateau, meaning they are not changing. They reach a plateau. Even if we increase more training data, nothing is changing, right? So we can see here that what is happening here, that the graph in the upper left shows that a model with high bias, meaning the model has low training and cross-validation accuracy, which indicate that it is underfitting. So this is the desired what you want, but the accuracy here is very low. Can you see? We expect to have something like this. So even on training data, can you see this is dot, 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 this is the training data. The accuracy is very low. It's not up to somewhere here, right? And even in the validation, the accuracy is maybe 0.3. Can you see that? So both on training data and test data, the validation, the accuracy is very low. So we can see that this model has a high bias, meaning it is both having low accuracy on both the training and test set. That is what they said, yeah. We can also see that if we have more data, we add more data, nothing is changing. So a model that you give it more data, but it's not learning anything, then that model also is high bias. Okay, this one, as we can see here, this is the number of training sample, but we can see here the training data. Remember, this is this is the number of training sample. Here, for example, we have 100. Here we have 200. Here we have 400, something like that. But you can see the training accuracy when we have small data. Maybe I have 10 training data, 10, and my model now has accuracy maybe 1.0. Perfect. You can see when I have 100, I mean 10. For example, let's assume that this data is 100. Now, when I have 10 here, you can see the training accuracy is perfect. Meaning on small data set, the training set is very high, meaning the model has memorized everything because it's very small data. But as you can see, the more I add more training sample, the performance of the model on training size decrease, right? So here, the model is even more overfitting because you're memorizing in all the field. So you remember one way to remove the problem of overfitting to add more training data. So we can see here, this is the desired performance. Maybe see here, the training error with reduce accuracy is reducing with more training sample, which is quite good. But we can also see the validation accuracy, because for validation, what we expect validation is like, we can see here for the validation also, yeah, it's increasing, it's small for validation. When you have small data set, it's small, but when you increase more data set, we can see the validation is increasing, which is small. But the problem here is that there is high variance, meaning the model maybe is overfitting the data, because you can see the difference between accuracy for the training set, the accuracy for the dev set is very large. So this means that this model has high variance, it's overfitting because it has higher accuracy. Maybe here is 90 for training side, for the training data, but for the development data, maybe the accuracy is maybe 60%. So you can see it has high variance. There is high variance here in this. Now, a good bias variance trade-off, this is what we want. This is the expected result you want, but the training accuracy and the validation accuracy, you can see that it's very small. The difference is very small. This is the good bias variance trade-off. So this is what you can use to, plot a model to see the curve that shows you whether your model has bias or has a good variance. So yeah, any question? And remember, when we are training this model, you have the same hyperparameter. You are just changing the number of the data set. Everything is the same, just changing the number of the data set.
Yes, sir. Can you give more light about the desired accuracy?
Oh, yeah. So the desired accuracy is like when let me see. Yes, so the desired accuracy, if you are training a machine learning model, maybe in some practical sense, you expect like, you don't want a model, you don't want performance to be less than 90%. Any model that gives you less than 90%, you don't want that one. So that is, you had you have like predefined accuracy you expect to have a good model. So any model that doesn't have this kind of predefined accuracy, you just, you just discard it and select another one. So yeah, so it just depends on different field. In some field, you can say accuracy. It depends on how difficult models your data modeling should be. So in some domain, you may have like your accuracy to be, you want 98. In some domain, you cannot at all having accuracy to be 98. Maybe the maximum accuracy you may have like 70 or 80. So it depends on how hard difficult the task is. If the task is not difficult, then you can expect to have 99 accuracy, something like that.
So if someone maybe published an article, maybe he has gotten maybe 98%, maybe the accuracy of the model. So now, can I set my desired accuracy just above 98%? Can I say 99.2345 etc?
Yeah. So yeah, if you desired accuracy, so this is not some kind of a thing that your model is doing. It is you that you define the accuracy you want. This is not for model. Machine learning model in one number. If you read the book, these two are the one that machine learning, the performance of machine learning model. Because for example, here you have your data 100 example, you train a model, and these are the point. For 200 you train a model, for 300 you train a model, for 400, and now you follow the performance of the accuracy by changing the training size. This one, it is you that you just put it, and it depends on, as I said, the
yes, I understand, but you see sometimes if someone maybe publish an article and maybe he's gotten maybe 98%, yes, you may propose another architecture, maybe neural network architecture, that you can outperform that accuracy. Yeah. So if someone maybe has gotten maybe 97% of accuracy, can I set my desired maybe accuracy to be 99 or something like that?
Yeah, so I think research, this is maybe in for somebody to set my desired accuracy, it boils down maybe, I think, in practical or deployment settings. But in research, I think all we want is we want to reach the highest, highest performance. We want to reach this bias variance trade-off. So I'm not sure, like in research, for example, you are saying, can you set like your desired accuracy to be better than another person's paper? Is that correct?
Yes, exactly.
Yeah, so that's what we always aim. We always aim to beat the current literature, the performance in the current literature. We always want to beat that. If somebody has 95, so if you come with 96 accuracy, then you are the better one. But provided your model is not overfitting, that's why you have a good bias variance trade-off. If the model is not overfitting and you beat that one, then you are good. So how can we do this learning curve in scikit-learn? So for you to do this, you can do them in scikit-learn. And yeah, so if, let me share this. Okay, let me see if I can also share my screen. Okay, let me reshare my screen with this. Okay, this one, scikit-learn, and no. Na biya squad ɗin take ne ma ta gudu. Okay. Oh, ashe ba ma daidai nake da ba. This guy plus this guy and plus this guy. Okay. Can you see my screen now? Can you see my screen?
Yes.
So can you see something called learning curve? So,
yes.
So this is what we can use in scikit-learn to do that. It generates a cross validation generator with the whole day, something like this. So let me show you how we can do that. So here you can see from scikit-learn model selection, I import learning curves, and now I create here our pipeline. I put my transformer, and now I put the logistic regression, which is final. Now here you can see I use a learning curve here. Can you see that? I imported model selection. I have my trend size, trend score, and test score. Because if you remember here, if you want to plot the learning curve, we put maybe training sample here, and now we plot training accuracy, we plot validation accuracy. So here you can see we have training size, right? Training size, which is this number of training size here that we're gonna have. We have a training score, which is this training score, and we have this test score, which is validation score, which is this one. So you can see this validation learning curve, what you need to give it, as I showed here. If you look at it, learning curve, you're gonna have like estimator. What is the estimator you're gonna use? The algorithm. So estimator, we're gonna use 5 LR that we use. This is our estimator because we do the this is our estimator, which is logistic regression, but we use this is the estimator. And now you see here, the next thing is you give the X train and the Y. X is the train, and here is the the target. So here, this is it. We give it this one here and this one here. And now here, the next thing is train size. You provide how you're gonna divide the data set. We use NumPy line space, meaning it can be 10 steps. So you put the how many. So learning curves also use cross validation. So CB is 10. So if you're gonna use learning curves, so because you remember we talk about cross validation. So we from now on, if we want to train a model, we will always be using cross validation. So we are not using this classical vanilla. Yeah, so we are always, so you can see cross validation score, cross validation. So the learning curve is using cross validation as well. Yeah, so you need to provide the CV, how many number, and the number of the jobs. Remember here, when we do the cross validation, you need to provide how many validation, how many times you want to, how many fold do you want. So we need 10 fold, number of jobs. So also they make, I think they make explanation here in the book. You refer the book that learning curve also use cross validation. So this is it. And now you can see here, remember here, the train scores, I find the mean here, what it returns. So you have the mean, and here I find the standard deviation, for the test. This is the training, this is the test mean, and this is the test standard deviation. Yeah, so this is train size. No. Oh, okay. This is the train. Can you see? I call the train scores, and this is the test mean. I call the test score here. And now here we can use these to basically do the plotting. So here we use fill, we provide the train size here. And here we can see we provide, we also plot train size and test mean. And now here we do the plot with fill between. So here you can see this is just basically, you can walk through the code. In our previous session, we discussed how we can use plot, matplotlib, and all this stuff. So you can see here, this is our algorithm, right? So here, the takeaway is basically telling us here, something new here is that learning curve, you want to see, you want to plot learning curve, you just use this function, and now this is what it returns. 3 things. Number 1, train size, train score, test score. And this is it. And now all the thing we are here is we are trying to do plotting to see this. So all this code is plotting. And now we can see here is, this is validation accuracy. This is the train accuracy. So you can see the training accuracy at the beginning, we have 50, the training number of training example 50 at the beginning. It memorized everything. It has 1% accuracy. Remember, because it's small data, the algorithm will memorize everything, right? But the validation accuracy, as we can see here, is so small, which maybe with because if the model is overfitting, remember what we need to do is add more data. So you can see when we add 100, the model is stop overfitting, is dropping, and the accuracy is of validation is increasing. Can we see? So it, you know, when we add maybe at 200, 150, you can see like the model is still coming down, and you know the accuracy here. So as we can see in our model performs quite well on both the training and validation set as if it has in this mode. So when the model exceeds 250 sample, we can see the model is doing well. Can we see that? Because it's not overfitting the data, but and the validation accuracy, you know, you can see this. Yeah. So as we can see, if it has more than 250 samples. So when we have more than 250 samples, you can see like the gap between training accuracy and validation accuracy is small. But we can see here the gap between validation accuracy and training accuracy is large. Then what does that mean? Who can tell us what is happening at this? What is happening with the model? Who can tell us what is happening at this when we have like between data between maybe 100 and to 100, we can see like there is a gap between accuracy of model on training.
We are increasing number of data. That is why it is decreasing.
Okay, so what is happening now? This gap is telling us what the gap between model training accuracy and validation accuracy. If we have huge gap, what does that mean?
From what I read, is overfitting.
Exactly.
Overfitting because
yes.
it learned very well.
Yeah. Yes, you are right. The model is overfitting because you can see. Remember when we have large.
I read it, but I don't understand what it means.
Yes. So what it means is that you can see like here the accuracy, for example, at this point. Okay, let's assume here at this point the accuracy is 1%. That is perfectly right. But the validation accuracy is 95, meaning there is huge gap between accuracy on training sets and the validation set. But if you have that kind of huge gap, then the model is overfitting. It's learning well, only very well on training set, but it's not learning very well on the validation accuracy. And what we want is, we want a very small difference between the validation training accuracy and the validation accuracy. For example, if this is 98, then the validation accuracy should be like 96 or 97. You know, it's not that. So, but we can see here when we have 400 examples here, the accuracy, is minimal. So with more data, if the model is overfitting here, with more data here, now the model is not overfitting, the model is doing well. So this is telling us when you have more data that you are reaching high bias variance trade of this guy. So you can see here, this is bias variance. Can you see this one? Can you see that? So this one, you can see we didn't define anything Falalu that this is the desired performance we want. We just say, okay, we just run our model. And so this is something. So this is telling us that the model with more data is doing well. But at the beginning, we can see that the model is, yeah. Anyone want to add something? Any question? Okay, so sani ba akwai an gane kuwa?
Ana ganewa.
Right. So another one shine da ake da shi is addressing overfitting and underfitting with validation curve. So here you can see what we show here is that accuracy and number of training example, right? So if you have accuracy and training example, we are addressing whether the model has high bias or high variance. So we can see that here there is a bias variance trade-off. But what if you want to addressing the issue of overfitting or underfitting with what we call validation curve. So this is called learning curve, because the more you add data, the more you have accuracy. Then you are trying to find how your model is learning. That is why it's called learning curve. The more what is the relationship between accuracy and the number of training example? You want to find the accuracy. So even you yourself, now you have training data, you are training your machine learning model. Try to do this to find at what point that your model is performing well. So from there you can say, now it means if I have training data from 400 to above, my model can do well. But if you have training data like 200, that it doesn't work. So it gives you how your model is learning based on the number of training examples. But let's see how we can also validate, understand the issue of overfitting and underfitting with validation curve. So validation curve are useful for improving performance by addressing issues such as this. So this is still the same thing, but here we import what is called a validation curve. Can we see that? Validation curve. But here what we import is called learning curve. Each learning curve is used. This one, it should be accuracy. This one is training example. But now what we import is validation curve. So the same thing with that, we have validation curve here. Can you see validation? And here we can see like we have training score and test score. So validation curve, what it will return is training score and test score. As we can see here, because we are not plotting training sample here. You can see here, because we are plotting number of training sample, we are plotting the training sample, we are plotting this, then that's why we have it returns three things here: the learning curve, training size, training score, and test score. But at the other one, what we are plotting is here the accuracy, and here you can see trends accuracy, you can see validation accuracy, but here we are not plotting training sample, we are just plotting parameters. So what does that mean? So we want to, for us to, if our model, we want to find the model is overfitting. One way to deal with the issue of overfitting, you remember, is regularization parameter, right? For example, for logistic regression, if you remember, it has a parameter for regularization. So if you use small regularization parameter, what happens if, so you can plot your model with these regularization parameters. For example, you use 0.001, which is this one, 0.01, which is this, 0.01, 0.1, shine sama and 10.1. So we plot our regularization parameter and see at what regularization parameter the model performs better. That is it. So this is what this means. So here you can see we have validation curve, and now we put everything the same thing like the learning curve, but here what we put is our parameter that we are going to use for the our regularization parameter. So here we want to plot regularization parameter and the accuracy. Remember, we always say that the regularization parameter, when we have small, it makes the model more complex. Well, when we have large, it makes the complex. We will see that. So this is still the same thing as previous that we have shown, all this stuff. Now let's look at it. So you can see similar to the learning curve, the validation curve function used stratified. So here it's used stratified also. We stratified sampling, and as the default, cross-validation by default to estimate performance. So it uses stratified k-fold cross-validation by default. And here you can see we provide some kind of the argument we want to regularize, which is parameter C. For logistic regression, we have parameter C. If you remember, for logistic regression, we have parameter C, which is the regularization parameter, and now we put the we put it, and now here you can see how many fold do we want? We want to use 10-fold. Yeah. So here you can see what will happen is that we can see like when we have C, regularization parameter is very small, then the accuracy, as we can see here, is somehow like this. But when we increase the C, we can see the accuracy is here. When we have maybe 0.1, we can see the accuracy is here. So this tells you that maybe the best C regularization parameter is temper, because you can see here, they have good performance at this point, right? At 0.1, which is parameter, they have good performance, and you know, the difference between them is very small. Or like here, when you have like 10^2, which is basically this 100, when you have C 100, you can see like the model here has a good performance on training side, but doesn't have on validation side. So here is overfitting, right? So you need to find a sweet spot where the model is doing good work on training set, and yeah. So that is it. Although the difference in accuracy for variant C is subtle, we can see that the model slightly underfit the data when we increase the regularization. So you can see when we increase the regularization here, 10^2, which is 100, the model is underfitting the data. It's not doing good job. However, for large, underfit the data when we increase the, okay, small value of C. Yeah, so here at this, when we increase the small value of C, when the value of C is very small, the model is underfitting, because you can see the training side and the validation side is not so well. But when we increase, at some point, yeah. So that is basically this called validation curve. It allows you to see which regularization parameter best for your model, so that you can just select it. So even though this is not the best approach to select regularization parameter, the next session, which is fine-tuning machine learning via grid search, will show us the best way to select maybe all these regularization parameters. But this is one way to just try to visualize your stuff. And you may see it in some papers, so it will make sense for you to understand it. Yeah, any question? I think it is already time. Any question? Okay. So if there is no question, what we have seen today is just like we went through the K-fold stuff, and we see how it works. And now we have seen this curve, which are very useful. When we start doing deep learning, you will start seeing this effect. Okay, you will understand, oh, the model is not good and stuff like that. So it's good you read this chapter and understand thoroughly what this means. Inshallah, tomorrow we'll see the final part, grid stage, and the other one, which is